Hi, so this is the second part of our lesson in projectile motion, and in this video we'll be having sample problems in projectile motion. We'll be solving problems on horizontally launched projectiles in projectile. We will also have projectiles that are launched at an angle. Let's dig right into our first problem. So a ball is thrown horizontally from the edge of the top of the building, 50 meters high, and it strikes the ground 24.5 meters from the foot of the building. So solve for the time it takes the ball to reach the ground, the initial velocity of the ball, and the velocity just before it hits the ground. We need to analyze our problem, and this is a problem where your object is launched horizontally. Now, the first variable we need to solve is time it takes for the ball to reach the ground. Now, if you remember, we have a formula that we derived during the first video that where time is equal to 2v0 sine theta, right, over g. But however, this will be not applicable because, again, those formula that we derived will be applicable for symmetric projectile motion, or when you divide the projectile motion, what happens on the other half or the first half is mirrored on the second half. In this case, since this is a horizontally launched projectile, then as you can see, it just looks like a half of a full projectile motion, or a projectile that's launched at an angle with respect to the horizontal. But do not worry, because we can use all of the kinematic equations, the one-dimensional kinematic equations, to solve problems in projectile. Because projectile is still kinematics, but just a combination of horizontal and vertical motion. So to solve for time, we need known values, right? So the ball, the time that the ball requires to reach the ground, which of course it will cover a displacement. And what will be the value of the displacement? So as you can see here, the ball drops to the ground from a 50-meter high building. Then therefore, the change in displacement or position of your ball will be negative 50 meters. Because from the top of the building, it went down. Therefore, the change in position is negative 50 meters because it went down. What else? Of course, you know g, which is negative 9.8 meters per second squared. Correct? And since this is a horizontally launched projectile, and since this is a projectile, this one starts at its maximum height. If you look at it, this is the maximum height of the object. So if this is the maximum height of the object, then it's also safe to conclude that your initial velocity along the y is 0, since that is horizontally launched. So we have here several values already, and we can solve for time using these three known variables. Now, what equation can we use? We can use y is equal to initial velocity along the y times time plus your 1/2 gt squared. Then you can just substitute your values there. That's negative 15 meters equals, of course, 0 time, because initial velocity along the y is 0, plus 1/2 gt squared. Or you need to substitute g, negative 9.8 meters per second squared times time squared. So since that is 0, then you can just leave it. Now, we need to rearrange our equation to solve for time, and the equation will be time will be equal to the square root of negative 50 meters over 1/2 times negative 9.8 meters per second squared. Then that will be equal to, time will be equal to the square root of negative 50 divided by 1/2 times 9.8. So that will give you a value for time of 3.19 seconds. So therefore, the time that it takes for the ball to reach the ground is 3.19 seconds. That's for A. Now for B, the initial velocity of the ball. So we need to solve for the initial velocity of the ball. And when we speak of the initial velocity of the ball, that's not just initial velocity along the x nor initial velocity along the y, but initial velocity, not components. So solving for the initial velocity, but to solve for the initial velocity, we will need its components. So your initial velocity in x and initial velocity in y. So your ball here is horizontally launched. Since it at its maximum height, and in our assumption in the first variable or in the first unknown problem, unknown variable that we solved, we already identified that initial velocity is 0. Now we just need to solve for the initial velocity in x. So what will be the value for the initial velocity in x? Remember that in projectile motion, a projectile motion is a uniform horizontal motion, which means that the velocity along the x-axis does not change because acceleration is equal to 0. If that's the case, then our assumption will be your initial velocity in x will also be equal to initial velocity to the final velocity in x. And if they are both equal, then your average velocity will be the same. And remember, your average velocity is equal to x over time. If the average velocity is equal to your initial velocity in x, then therefore initial velocity in x is equal to x over time. And we know that your x is 24.5 meters. As you can see here, 24.5 meters divided by the time. Remember again as well that the time it requires for an object to cover its displacement along the y-axis will also be the same will also be the same time the object requires to cover the x-axis. So therefore, 3.19 seconds is not just the time the ball, or it's not just referring to the time the time it takes the ball to reach the ground, but it's also the time the ball reaches or covers its displacement along the x. So 24.5 divided by 3.19, then that will give you an initial velocity in x, which is 7.68 meters per second. But that's not yet our final answer, because what we're solving is your initial velocity. And since you have your x and y component, then you can just use the Pythagorean theorem. So your initial velocity in x squared plus initial velocity in y squared. So substituting your values, you have 7.68 meters per second squared plus 0 squared. So 0 squared is 0. Now, you're only left with 7.68 meters per second squared and the square root of it. You can just cancel square root and square. So you're left with 7.68 meters per second. Therefore, the initial velocity is 7.68 meters per second. Okay? So this is your initial velocity. Now, question C, the velocity just before it hits the ground. So you will solve for the velocity of this object just before it hits the ground, which is at this point here. So from the top of the building, the ball is now here, and we will solve for its velocity just before it stops. So this one. Now, how do we solve for that? Again, we will still need your components. Now, we have mentioned earlier that your initial velocity in x. These are the values that we already have solved. And we also have identified that your initial velocity in y is 0 and your initial velocity in x is 7.68 meters per second. If that's the case, if you remember, we mentioned that your initial velocity in x is equal to the final velocity in x because, again, projectile motion follows along its x-axis. It's a uniform horizontal motion. So therefore, this is 7.68 meters per second as well. Now we need to identify the final velocity in y. So how do we solve for the final velocity in y? We know the time. We also know the initial velocity along y. And remember that we also know g, right? Which is negative 9.8 meters per second squared. But one simple equation that we can use for that is this one. A is equal to final velocity minus initial velocity times time. And just changing the values there to fit the dimensions that we are solving, which is in y, then this equation can be transformed into g is equal to your final velocity in y minus initial velocity in y over time. Now, since initial velocity in y is 0, then you're left with g is equal to final velocity times time. So to solve for the final velocity, rearranging your equation, we get final velocity in y is equal to g times time. Substituting your values, that's negative 9.8 meters per second squared times time, which is 3.19 seconds. So you cancel that. Therefore, your final velocity in y is negative 9.8 times 3.19. So that will give you a value of negative 31.26 meters per second. So therefore, the initial velocity in y here is negative 31.26 meters per second. Of course, it makes sense because it's going down. And the initial velocity in x is 7.68 meters per second. So to solve for the final velocity, of course, it follows. We can use the Pythagorean Theorem where your final velocity in x squared plus final velocity in y squared, the sum of the squares of the components, then you take the square root, then you'll get the value for velocity. Substituting your values, you have your final velocity in x, or the x component, which is 7.68 meters per second squared, plus for the y, it's negative 31.26 meters per second. So you square that as well. Now your v will be equal to, solving 7.68 squared plus negative 31.26 meters per second squared. Then we have a value for our final velocity, which is 32.19 meters per second. So this is our magnitude for the final velocity. But of course, we need to solve for the direction. The direction for the initial velocity of the ball, the direction was horizontal or at 0 degrees because it was launched horizontally. Therefore, the direction was 0 degrees. But for this one, we know that it's not. So we need to solve for the angle here. This one. So to solve for the angle, so it still follows theta is equal to inverse tangent to your velocity in y times velocity in x. Tangent, inverse or inverse tangent. Inverse tangent of your y is 31.26 meters per second over 7.68 meters per second. That's 31.26 divided by 7.68. Then the direction will be 76.2 or 76.2 degrees below the horizontal. Therefore, your final velocity is 32.19 meters per second, 76.2 degrees below the horizontal. Take note of that. It's below the horizontal. So that is or these are our answers for the first problem, which is a horizontally launched project. Next, we have our next problem. So our next problem, we have here a projectile that's launched at an angle. An object is launched at a velocity of 20 meters per second in a direction making an angle of 25 degrees upward with the horizontal. So we have four unknown variables to be solved. What is the maximum height reached by the object? What's the total time of flight? What's the horizontal range? And what's the magnitude of the velocity of the object just before it hits the ground? So let's start with solving our unknown variables. So the first one, it's the maximum height. So what's an equation that we can use to solve for the maximum height? If you look at our problem, if you look at our projectile, it's symmetrical. Therefore, we can use the derived equations that we have in the previous video. So what is a formula to solve for, or what's the derived formula for us to solve for h max? You have your height, which is equal to your initial velocity squared sine squared theta over 2g. So with this equation, you can just substitute your known variables because you already know your initial velocity, which is 20 meters per second, your angle of launch, which is 25 degrees, and of course, your g here. Remember, in our derived equations, your g already factored in the negative. So that's 9.8 meters per second squared. Okay? So substituting your values, you have 20 meters per second squared, and then sine 25 squared over to 9.8 meters per second squared. So inputting that, you have 20 squared times sine 25 squared divided by 2 times 9.8. Then you'll get a value of 3.645. Since that's height, of course, that will be meters. So the maximum height of the projectile is 3.645 meters. Now let's solve for B. The question in B is the total time of flight. Now again, we also have derived an equation for the time of flight in this kind of problem, where the time of flight is equal to 2v0 sine theta launch angle divided by g. And then you just substitute your values. That's 20 meters per second times sine 25 degrees over 9.8 meters per second squared. So that's 2 times 20 times sine 25 divided by 9.8. So that will give you the total time of flight, which is 1.72 seconds. So this is your time of flight. Okay. Now, letter C. So for letter C, we are to solve for the range. So what's the range of the object? And we also have a derived equation for the range of a symmetrical projectile motion, which is range is equal to your initial velocity squared sine 2 theta over g. So what you need to do is to, again, substitute the values where initial velocity is 20 meters squared times sine. Again, when you input this in your calculator, make sure that you double the angle first before taking the sine, because you might input it where you only get the sine of 2 and then you multiply it by the angle. So what you do here is actually you double the sine of 2 times the angle, which is 25, over 9.8 meters per second squared. So that's 20 times the sine of 25 times 2 is, of course, sine of 50 divided by 9.8. So that's 20 squared times sine 50 divided by 9.8. So your range will be 31.27 meters. So that is the range of the object. So a recap, we already solved for your maximum height, and your maximum height is 3.645 meters. Your range is 31.27 meters, and the time of flight is 1.72 seconds. Okay, now for the last question, we have here D, which is the magnitude of the velocity of the object just before it hits the ground. So this is the question. Now, remember that projectile motion also follows the symmetries in free fall. So, if the initial velocity is 20 meters per second, if the magnitude of the initial velocity is 20 meters per second, at the same point, going down, that will also be 20 meters per second. That follows your speed symmetry. So therefore, the magnitude of the velocity just before it hits the ground is also 20 meters per second. So those are our answers for the problem, or our second problem, which is a problem launched at an angle with respect to the horizontal. So we're down to our last problem in projectile motion. This is still projectile launch horizontal. This is still a projectile launch at an angle, but we have here an inclined plane. So a projectile is launched from point O at an angle of 22 degrees with an initial velocity of 15 meters per second up in an inclined plane that makes an angle of 10 degrees with the horizontal. So the projectile hits the inclined plane at point M. So the question is for us to solve for the time that the projectile hits point M and the distance between points O and M. So what do we need to do here? What we can do here is actually to find a relationship between your X and Y components. Oops, let me rewrite that one. Between your X and Y components. So this is your X and this is your Y with respect to the final position of the object. Now, we have here an angle that gives us a connection between these X and Y. Now, the angle with respect to X, X is the adjacent of the angle, while Y is the opposite of that angle. And when you have adjacent and opposite and an angle, then we can actually make a relationship with a mathematical relationship with the use of the trigonometric functions, specifically tangent, because tangent theta is equal to y over x, or opposite over adjacent, right? So we have here tangent 10 degrees is equal to y over x. Now, we also know that your initial velocity can be broken down into your components. So you have initial velocity, which is 15 meters per second at 22 degrees. But there's a question on what angle to use. Is it 22 or is it 10? So remember that we are looking into, or we have factored in the x component or the displacement in x along the horizontal. So therefore, we need to combine your angle. So if your angle 1 is 10 degrees and angle 2 is 22 degrees, then the angle that we need to use is 32 degrees. So to solve for the x component of 15 meters per second, so that will give you initial velocity times cosine angle 3. We'll be using angle 3. And for your y component, that's v0 sine angle 3. We are asked to solve for the time. Now, what equations can we use? For this one, we will actually have to use the relationship between the x and y, which is tangent theta, which is equal to y over x. Now, we need to have an equation where we can express y and x into time. And this equation is x is equal to v0, x, of course, this is x component, times time, plus 1/2 acceleration in x times time squared. Now remember that acceleration in x is 0 because in projectile motion, your horizontal motion is a uniform horizontal motion. Therefore, acceleration is equal to 0 and the velocity does not change. So therefore, your x is equal to your component or initial velocity in x is v0 cosine angle 3 times. Now for your y, so y is equal to v0y times time plus 1/2 ay t squared. Defining further or expanding further your variables here, you have v0 sine theta because your initial velocity in y is also expressed as initial velocity sine theta 3 times time plus 1/2. Your acceleration in y is also g, correct? Because it's free fall, times t squared. So you now have an equation for x and y where it is expressed in time. So what we need to do here now is just to substitute. So let's just make a division there so that we don't get confused. So we have here your tangent 10 degrees is equal to y over x. And your y here, y is v0 sine angle 3 time plus 1/2 gt squared over your x, which is v0 cosine angle 3 times time. So you can actually cancel this one. Now, rearranging your equation, you get, if we transpose this one to the other side, then we get v0 cosine angle 3 times time times tangent 10 degrees, which is equal to v0 sine theta 3 times time. Oops, it's already, we already canceled out the time, plus 1/2 gt. So we are left with time in this expression. So to arrange the equation, we need to rearrange the equation to have just time in one side of the equation. So time will be equal to, you can transpose this one first. So you'll get v0 cosine theta 3 times tangent 10 degrees minus V0 sine angle 3 over 1/2 G. When you transpose that, it becomes negative, or it becomes division. So if we substitute values here, then you get 15 meters per second times cosine 32 degrees times tangent 10 degrees minus 15 meters per second sine 32 degrees over 1/2 negative 9.8 meters per second squared. So keying that in our calculator, so that's 15 times cosine 32 times tangent 10 minus 15 times cosine, or that's sine 32 divided by 1/2 times negative 9 point. So the time is 1.16 seconds. So the time that it takes for the object from point O to hit point M is 1.16 seconds. Okay? Now, that's for letter A. For letter B, we need to solve for the distance between point O and point M. So how do we solve for the distance between point O and point M? Remember that your resultant can be solved using the components with the Pythagorean theorem. So let's, now for B, find distance OM. So that's B, OM is a no. Now if we recall the expressions that we have for X and Y, we have X, which is equal to your initial velocity cosine angle 3 times time. And your y is your initial velocity sine angle 3 times time plus 1/2 gt squared. Okay? Now, your OM, since we have your x and y components, here you have your x and y components, this point here, we can actually solve it using the Pythagorean theorem, where OM is equal to the square root of x squared plus y squared. So for us not to be burdened by so much expressions here, we can actually solve for x and y at this point. So for x, let's have x is equal to V0 cosine angle 3 times time. So substituting your values, you know that initial velocity is 15 meters per second times cosine, that's 32 degrees times time, which is 1.16 seconds. We already solved for the time in A, which is time is 1.16 seconds. So x is 15 times cosine 32 times 1.6. So that gives you the value for x, which is about 14.7560 meters. That's approximately 14.7560. 15 cosine 32 times 1.16. Now for y, so y is V0 sine theta 3 plus 1/2 gt squared. If you substitute your values for that one, you have 15 meters per second times sine 32 degrees times 1.16 seconds plus 1/2 g is negative 9.8 meters per second times 1.16 seconds squared. Now, putting that all in your calculator to solve for y, then that's 15 sine 32 times 1.16. So 15 sine 32 times 1.16 plus 1 half, or that's 0.5, times negative 9.8 times 1.16 squared. And that will give you approximately 2.6272 meters. So if that is x and that is y, then you can solve for OM, which is your x is 14.7560 meters squared. Let me just rewrite that one for much space. So that's OM is equal to the square root of 14.7560 meters squared plus that's 2.6272 meters squared. So OM will be equal to, that's the square root of 14.7560 squared plus 2.6272 squared. Then that will give you a value of approximately 15 meters. Therefore, the distance between points O and M is 15 meters. So that's it for our sample problems for projectile motion. So again, projectile motion can be horizontally launched or launched at an angle with respect to the horizontal. I hope you have understood well our lesson in projectile motion, and we have also had a practice on how to solve variables in word problems involving projectile motion. So see you in our next lesson. Bye!